The phenomenon of light is very mysterious because on one level, it really defines our reality. It's maybe the most defining characteristic of our reality, as everything we see and how we perceive reality is based on light bouncing off of objects or bending and refracting around objects and then being sensed by our eyes, which send signals into our brain that create models of the world we see around us. So it really is almost a defining characteristic of our reality. But when you really go down to experiment and observe with life, it starts to have a bunch of mysterious properties, and to a large degree, it is not fully understood yet. Probably the most amazing thing about light is actually not just true of life. This is actually true of almost anything once you get to a small enough quantum mechanical level. So light behaves as both a wave and a particle, and this is probably not that intuitive to many people. We're used to certain things behaving as waves, like sound waves or the waves of an ocean, and we're also used to certain things behaving like particles, like houses or phones. We're not used to things behaving as both, and it really depends on what experiment you run and how you observe light. So when you observe it as a particle, this comes out of Einstein's theory with the photoelectric effect. You can view light as a train of particles moving at the speed of light, and we call these particles photons. If you view light in other ways, you see it even when you see light being refracted by a prism. Here, it looks like it is a wave. It has the properties of a wave, which means it has a frequency and a wavelength, and like other waves, the velocity of that wave is the frequency multiplied by its wavelength. Now, even if you ignore this particle aspect of light, if you just look at the wave aspect of light, it's still fascinating because most waves require a medium to travel through. So for example, if I think about how sound travels through air, what happens is it compresses some of the air particles, and those compress the ones next to them, and so you have these points in the air that have higher and lower pressure than one another, and you can plot that. So we have high and low pressures alternating between the waves of light, and as these things bump into each other, this wave essentially travels to the right, and if you were to plot that, you would see this wave form traveling to the right. But this is all predicated upon this energy traveling through a medium, and we're used to visualizing waves in that way, but light needs no medium. Light will actually travel fastest through nothing. In a vacuum, light will travel at an unimaginably fast speed of 300,000 kilometers per second. And just to give you a sense of this, light can go around the Earth more than 7 times in 1 second, so it's definitely unimaginably fast. Not only is this just a super fast speed, it once again tells us that light is something fundamental to our universe, because it's not just a fast speed, it is the fastest speed known to physics, but possible in physics. So once again, something very unintuitive to us in our everyday lives. We used to imagine that if something is going at some speed, maybe if there's an ant, for example, riding on top of it, when it's moving in the same direction, it would be going even faster. But nothing can go faster than the speed of light. It's absolutely impossible based on our current understanding of physics. Now, within the visible light spectrum, you're probably familiar with many of the possible colors. Maybe imagine them as the colors of the rainbow. And rainbows really happen because the white light from the sun is being refracted by the water particles. And you can see that in a clearer way when you see light being refracted by a prism like we can see here, and the different wavelengths of light. White light contains all of the visible wavelengths, but the different wavelengths get refracted differently by a prism. So in this case, the higher frequency wavelengths of violet and the blues get refracted more, and it gets bent more than the low frequency wavelengths of the reds and the oranges. The wavelengths of the most visible light lies between 400 to 700 nanometers, and the higher the frequency, the higher the energy of that light. That actually goes into when you start talking about the quantum mechanics of it, and that the higher frequency means each of these photons have higher energy, which implies that they have a better ability to give kinetic energy to knock off electrons. So I keep referring to this idea of the visible light, and you might say, what is beyond visible light? What you'll find is that light is just a part of a much broader phenomenon. The part that we happen to observe is really just a part of the electromagnetic spectrum. So light is really just electromagnetic radiation. Everything that I've told you about light just now has a wave property, and it has particle properties. This is not just specific to visible light, this is true of all electromagnetic radiation. So at very low frequencies or very long wavelengths, for example, are things like radio waves, which are the things that allow radio channels to reach your car and allow your cell phone to communicate with cell towers. Infrared light is the light that your body releases, and that's why you can detect people through walls with infrared cameras. Ultraviolet light, also known as UV light, coming from the sun, will give you sunburns, and X-rays, which is the radiation that allows us to see through soft material and just visualize the bones. Gamma rays are super high energy that comes from supernovas and other certain types of physical phenomena. All of these types of light are part of the exact same thing. We just happen to perceive certain frequencies of this as visible light. You might still be asking, how come we only perceive certain frequencies of electromagnetic radiation? How come we only see these frequencies? The reason for that is that's the frequency where the sun dumps out a lot of electromagnetic radiation. So it's inundating the Earth, and if as a species we wanted to observe things based on reflected electromagnetic energy, it is easiest to perceive the things where there is the most electromagnetic radiation. So it is possible that in other realities or other planets, there are species that perceive more in the ultraviolet range or the infrared range. And even on Earth, there are some animals like snakes and fish that perform better at either end of the range. But we see really well in the part of the spectrum where the sun just happens to dump a lot of radiation on us. So I'll leave you there, as I think that's a pretty good sized overview of light. If any of this stuff seems kind of unintuitive or daunting, or really on some level confusing, this wave-particle duality, or this idea of a transfer of energy through nothing, don't worry, because it seems unintuitive even for the best of astrophysicists. We'll continue looking at the properties of light and the fundamental forces of our universe in the next video. But for now, I thank you all for watching.